Hello, sleepy genius. The day has asked much of you, and now the night offers stillness. Let your breath slow, your thoughts drift. Tonight, we explore a question both impossible and inevitable, a cosmic echo that lives in theory and mathematics. What if the Big Bang happened again? Rest now and wonder. From altering the speed of light to reversing gravity, from breaking the fundamental laws of physics to having every atom in our bodies instantly reconstructed. Tonight, we dare to ask the impossible. Could the universe as we know it be born all over again? Before our journey begins, if these curious facts help you rest and leave a weary day behind, a simple like or subscribe helps others drift here too, one soul at a time. Please, share your thoughts below. Now, let's begin. Every atom in your body would cease to exist in the first trillionth of a second. Picture yourself standing in your room, familiar and solid, when suddenly the space between your atoms begins to expand faster than light itself, in less time than it takes light to cross a single proton. The electromagnetic forces holding your molecules together would snap like overstretched threads. Physicists at CERN calculated in 2018 that temperatures would reach 10 to the 32nd power Kelvin within the first picosecond, a heat so intense that matter as we know it cannot exist. Every chemical bond, every structure, every memory encoded in neural pathways would dissolve into a soup of fundamental particles. To think that the solid world we trust is held together by forces that could unravel in an instant, returning us to the cosmic beginning. The entire observable universe would compress into a space smaller than a grain of sand. Consider the 93 billion light-years of space we can see, containing 2 trillion galaxies, each with hundreds of billions of stars, all collapsing inward at incomprehensible speed. Research from the Max Planck Institute in 2019 modeled this compression, showing that within the first microsecond, all the matter and energy in the universe would occupy a region smaller than an atomic nucleus. At this density, a teaspoon of this primordial substance would weigh more than all the mountains on Earth combined. Gravity would become so intense that it curves space-time into dimensions we cannot perceive. This reminds us that the vast cosmos we gaze upon is, in cosmic terms, already an explosion in progress, still expanding from that first incomprehensible moment. Time itself would restart, erasing every second that ever passed. Imagine standing at midnight on New Year's Eve, but instead of the clock striking 12, the clock dissolves, along with yesterday, last year, and every millennium before. Einstein's equations, verified by atomic clocks aboard GPS satellites with nanosecond precision, show that time is woven into the fabric of space-time itself. If space-time collapsed and reformed, time would reset to zero. Cosmologist Stephen Hawking wrote in 1988 that asking what happened before the Big Bang is like asking what lies north of the North Pole. Every historical event, every extinct species, every word ever spoken would exist in a timeline that no longer exists. In a sense, the past would become more than forgotten. It would become impossible. All the laws of physics would temporarily cease to function. Picture a world where gravity suddenly releases its grip, where light travels at random speeds, where cause no longer leads to effect. During the Planck epoch, the first 10 to the negative 43rd power seconds after a Big Bang, temperatures exceed 10 to the 32nd power Kelvin, conditions so extreme that quantum mechanics and general relativity both break down. Theoretical physicists at Princeton in 2016 demonstrated that at these energies, the 4 fundamental forces: gravity, electromagnetism, strong and weak nuclear forces merge into a single unified force that behaves in ways we cannot predict. The universe becomes a quantum foam of possibility, where particles blink in and out of existence without determinism. To think that order, predictability, and natural law are not eternal truths, but emergent properties of a cooling cosmos. Every black hole in the universe would evaporate in a flash of radiation. Consider the supermassive black hole at the center of our galaxy, Sagittarius A*, which contains 4.15 million times the mass of our Sun in a space smaller than Mercury's orbit. If space-time itself began to boil and expand as in a new Big Bang, the event horizons of all black holes would unravel. Research published in Physical Review Letters in 2020 calculated that the intense energy density of the early universe would cause even the largest black holes to release their captured matter and energy in bursts of Hawking radiation lasting mere fractions of a second. Trillions of years of accumulated mass would pour back into the cosmos. This reminds us that even the universe's most permanent seeming structures are temporary patterns in the flow of energy. The speed of light might have a completely different value. Imagine a universe where light crawls at the speed of sound, or races at infinite velocity, making every star visible instantly. In our universe, light travels at exactly 299,792,458 meters per second in vacuum, a constant that determines the relationship between energy and mass. But theoretical work by Joe Maguire at Imperial College, London in 2016 suggests that in the earliest moments after the Big Bang, the speed of light may have been different, perhaps variable. If a new Big Bang occurred, there's no guarantee the fundamental constants would reset to the same values. Light might move faster or slower, altering chemistry, nuclear fusion, and whether stable atoms could even form. In a sense, the universe we inhabit is one possibility among infinite configurations, most of which would be lifeless. Gravity could reverse, causing everything to repel instead of attract. Picture dropping a stone and watching it accelerate upward into the sky, faster and faster until it vanishes. While this seems impossible, cosmologists at Cambridge University in 2017 explored scenarios where the gravitational constant could theoretically flip sign during the chaotic conditions of a new cosmic origin. In such a universe, matter would scatter rather than clump, preventing the formation of stars, planets, or any structure at all. Gas clouds would disperse, never collapsing under their own weight to ignite fusion. The universe would remain a cold, dark, eternally expanding void of isolated particles. To think that the gentle pull bringing us back to Earth is not inevitable, but a feature of our particular cosmic beginning. All information would be destroyed, including every thought you've ever had. Consider that your memories exist as specific patterns of neural connections encoded in the physical structure of your brain's 86 billion neurons. Research from MIT in 2019 showed that memories are stored in the precise configuration of synapses, which depend on molecular bonds held together by electromagnetic forces. In the first instance of a new Big Bang, temperatures would ionize all atoms, destroying every molecule and erasing every pattern. Not just your memories, but every book ever written, every piece of data stored on every computer, every fossil record, every photon carrying information from distant galaxies would dissolve into a structureless plasma. This reminds us that consciousness, culture, and history are impossibly fragile arrangements of matter. persisting only because the universe has cooled enough to allow complexity. The cosmic microwave background radiation would vanish instantly. Imagine looking up at the night sky and seeing nothing. No stars, no galaxies, not even the faint afterglow of ancient light. This radiation, discovered by Arno Penzias and Robert Wilson in 1964, is light that has traveled for 13.8 billion years, stretched by expansion into microwaves that fill all of space at a temperature of 2.725 Kelvin. It's the oldest light in the universe, a baby picture of the cosmos when it was only 380,000 years old. If a new Big Bang began, this ancient light would be swallowed by the explosion, replaced by a new fireball of creation. Astronomers at the European Space Agency calculated in 2018 that within a single second, every photon in the observable universe would be thermalized into a new uniform glow. In a sense, we live inside the fading echo of our universe's birth, and that echo could be silenced in an instant. Electrons might become positively charged and protons negatively charged. Picture an atom where the nucleus orbits around the electrons instead of the other way around, where electricity flows backward, where chemistry operates in reverse. While this seems absurd, particle physicists at SLAC National Accelerator Laboratory in 2015 confirmed that charge is a property assigned during the earliest moments after the Big Bang through a process called spontaneous symmetry breaking. In the extreme energies of a new cosmic beginning, these properties could be reassigned differently. If electrons gained positive charge, they would repel each other rather than form stable shells around nuclei. No atoms could form, no molecules, no chemistry, no life. To think that the basic characteristics of matter are not intrinsic but chosen randomly from the chaos of creation. The vacuum of space itself could decay into a lower energy state. Consider that even empty space contains energy, a quantum foam of virtual particles popping in and out of existence. Theoretical work by Sidney Coleman at Harvard in 1977 proposed that our vacuum might be in a false vacuum state, like a ball balanced on a hill rather than resting in a valley. If a new Big Bang triggered a vacuum decay, space itself would transform, releasing tremendous energy as it dropped to a true vacuum state. This transformation would propagate outward at the speed of light, a bubble of new physics consuming the old universe, making current matter unstable. Research published in 2018 by physicists at Oxford calculated that stars, planets, and atoms would dissolve as this bubble passed. This reminds us that even nothingness has structure, and that structure could change. Dark matter might not form, leaving galaxies unable to exist. Imagine a universe where stars are born but never gather into spirals or clusters, just lonely fires scattered in endless darkness. Dark matter, which makes up 85% of all matter in our universe but doesn't interact with light, provides the gravitational scaffolding for galaxies to form. Observations from the Hubble Space Telescope in 2019 showed that without dark matter's gravity, normal matter would have dispersed too widely after the Big Bang for stars to ignite. If a new Big Bang didn't produce whatever particle constitutes dark matter, possibly ixions or neutralinos, the universe would contain only isolated stars drifting in a void. Astronomers at Yale calculated that intelligent life would be impossible in such a universe, as complex chemistry requires the dense environments found in galaxies. In a sense, we exist because invisible matter once clumped in just the right way. Antimatter might dominate instead of matter, annihilating everything we know. Picture a universe where every particle you're made of has the opposite charge, where antimatter galaxies drift through antimatter space under antimatter stars. In our universe, matter slightly outnumbered antimatter in the first second after the Big Bang, at a ratio of roughly 1 billion and 1 matter particles to 1 billion antimatter particles. When they annihilated each other, that tiny excess of matter survived to form everything that exists. Research at CERN in 2017 measured the properties of antihydrogen and found it identical to hydrogen except for reversed charges. If a new Big Bang produced slightly more antimatter instead, the resulting universe would be physically identical, but composed of opposite particles. To think that our entire existence resulted from a 1 in a billion asymmetry in the first instant of time. All planets and stars would evaporate before they could form. Consider the billions of years it takes for dust clouds to collapse into stars, for nuclear fusion to ignite, for planetary systems to stabilize. If the expansion rate after a new Big Bang were even slightly faster, gravity would never overcome the outward motion. Cosmologists at UC Berkeley in 2016 calculated that if the expansion rate were just 1% higher in the first second, matter would spread too thinly for gravitational collapse. The universe would contain only a dilute gas, growing cooler and more diffuse forever, approaching absolute zero without ever forming a single star. No fusion would occur to create heavy elements, no planets to orbit, no chemistry to begin. This reminds us that existence requires an impossibly precise balance between expansion and gravity, and that balance might not recur. Three-dimensional space might not reform, creating a universe with more or fewer dimensions. Imagine trying to point in a direction that isn't up, down, left, right, forward, or backward, but in an entirely new direction perpendicular to all of them. String theory, developed at Princeton and Cambridge in the 1980s, suggests that our universe may have started with 10 or 11 dimensions, most of which curled up smaller than atoms during the first 10 to the negative 35th power seconds. If a new Big Bang occurred, a different number of dimensions might remain large. Research published in Physical Review D in 2019 showed that in a universe with 4 spatial dimensions, atoms would be unstable and electrons would spiral into nuclei. In 2 spatial dimensions, complex molecules couldn't form. To think that the 3-dimensional stage on which all life performs might be one choice among many, and perhaps not the only viable one. The electromagnetic force could be weaker, making chemistry impossible. Picture atoms where electrons drift hundreds of times farther from the nucleus, unable to overlap with other atoms to form bonds. The electromagnetic force, carried by photons, determines how strongly electrons are bound to atomic nuclei. Calculations by Paul Dirac in 1937, later refined at MIT in 2008, showed this force is characterized by a constant called the fine structure constant, approximately 1 divided by 136. If a new Big Bang produced a universe where this constant was even slightly smaller, electrons would orbit so far from nuclei that molecules couldn't form. Water, proteins, DNA, all impossible. If the constant were larger, electrons would be bound so tightly that chemistry would proceed to slowly for life. In a sense, the richness of the material world depends on a single number falling in a narrow range. Time could flow in multiple directions simultaneously. Consider that you experience time flowing from past to future, entropy increasing, eggs breaking but never spontaneously reassembling. But research by Sean Carroll at Caltech in 2016 suggests that the direction of time emerges from the low entropy state of the Big Bang. If a new Big Bang produced a different initial configuration, time might not have a single direction. Theoretical models show universes where some regions experience time flowing forward while adjacent regions experience it flowing backward, or where time branches like a river delta, cause and effect would lose meaning, as events could influence their own past. To think that the linear progression from birth to death is not inevitable, but a feature of our particular universe's initial conditions. All the hydrogen in existence would fuse instantly into iron. Imagine every star in the universe burning through its entire fuel supply in a single second, completing billions of years of fusion in an instant. If a new Big Bang created temperatures even slightly higher than our universe's initial state, around 10 to the 13th power Kelvin instead of 10 to the 12th power in the first second, protons would have enough energy to overcome electromagnetic repulsion and fuse uncontrollably. Research from Los Alamos National Laboratory in 2018 calculated that this runaway fusion would convert all hydrogen directly to iron, the most stable nucleus. No hydrogen would remain for water or organic chemistry, no long-lived stars to provide steady energy for planets. The universe would glow brilliantly for a brief moment, then fade to eternal darkness. This reminds us that the slow burn of stars depends on the universe cooling at just the right rate. Every galaxy would collide with every other galaxy simultaneously. Picture the orderly cosmos we observe, where galaxies drift apart, carried by cosmic expansion, occasionally merging over hundreds of millions of years. If a new Big Bang produced less expansion or more matter, gravity would dominate and the universe would recollapse almost immediately. Simulations run by astronomers at Heidelberg University in 2017 showed that in such a scenario, all matter would fall back together within seconds or minutes, creating a cosmic traffic accident of unimaginable scale. Stars would pass through each other, gas clouds would collide at relativistic speeds, supermassive black holes would merge in cascading pairs. The energy released would heat the universe back to near Big Bang conditions. In a sense, the expansion of space is the only thing preventing the universe from crushing itself. Quantum mechanics might not exist, making matter predictable but lifeless. Consider that the uncertainty principle allows electrons to tunnel through barriers, enables mutations in DNA, permits quantum effects that make chemistry dynamic. Research by Werner Heisenberg in 1927, verified in countless experiments since, shows that you cannot simultaneously know a particle's position and momentum with perfect precision. This uncertainty is fundamental to how atoms work. If a new Big Bang produced a universe without quantum mechanics, electrons would spiral into nuclei following deterministic paths. Atoms would collapse, and matter would exist only as nuclear sludge. Theoretical work at Stanford in 2019 showed that biological processes, from photosynthesis to cognition, rely on quantum effects. To think that the strange, probabilistic nature of reality isn't a flaw, but a requirement for complexity and life. The strong nuclear force could be weaker, causing all nuclei to explode. Imagine every atomic nucleus in your body tearing itself apart, protons repelling each other with electromagnetic force, no longer held together by the strong force. This force, mediated by particles called gluons, binds quarks into protons and neutrons, and binds those into nuclei against electromagnetic repulsion. Measurements at Brookhaven National Laboratory in 2015 showed the strong force operates over distances of about 10 to the negative 15th power meters. If a new Big Bang produced a slightly weaker strong force, only hydrogen nuclei would be stable. No carbon, oxygen, nitrogen, none of the elements essential for chemistry and life. The universe would contain only primordial hydrogen and helium, unable to form complex structures. This reminds us that the atoms we're made of exist in a precarious balance of forces. Photons might have mass, making light travel at different speeds through space. Picture sunlight taking years to reach Earth, or different colors of light arriving at different times from distant stars. In our universe, photons are massless and always travel at exactly the same speed in vacuum, a cornerstone of relativity. But experiments at the University of California in 2018 measured the mass of the photon to be less than 10 to the negative 54th power kilograms, effectively zero but not proven to be exactly zero. If a new Big Bang gave photons even a tiny mass, electromagnetic radiation would behave differently. Low-energy radio waves would travel slower than high-energy gamma rays. The electromagnetic force would have limited range, like the weak nuclear force. Atoms might not radiate energy, making stars impossible. In a sense, the entire visible universe exists because light has no weight. The cosmological constant could be larger, tearing atoms apart through accelerating expansion. Consider that space itself is expanding, carrying distant galaxies away from us faster and faster. This acceleration, discovered by Saul Perlmutter and Adam Rees in 1998, is driven by dark energy, a property of space itself quantified by the cosmological constant. Our universe's constant is extraordinarily small, about 10 to the negative 52nd power per square meter. If a new Big Bang produced a constant just 10 times larger, calculations from the University of Oxford in 2019 showed that expansion would accelerate so violently that within millions of years, space between atoms would grow faster than electromagnetic forces could hold them together. Molecules would rip apart, then atoms, then nuclei, until the universe consisted only of isolated elementary particles in an ever-expanding void. To think that gentle cosmic expansion could become a force that shreds reality itself. Neutrinos might interact strongly with matter, making the universe opaque. Imagine a cosmos where light cannot travel, where every photon is absorbed within meters, where stars are invisible cocoons of energy. Neutrinos, nearly massless particles produced in nuclear reactions, barely interact with matter. Trillions pass through your body every second from the sun without touching a single atom. Experiments at the Super Kamio Kondi detector in Japan between 2015 and 2018 confirmed that neutrinos interact so weakly that one could pass through a light year of lead with only a 50% chance of collision. If a new Big Bang produced neutrinos with stronger interactions, the universe would be filled with a fog of particles that absorb all radiation. No light-based chemistry, no photosynthesis, no vision, no astronomy. Intelligence might never arise because information couldn't travel far. This reminds us that transparency of space is not obvious, but depends on specific particle properties. Protons might decay in seconds instead of being nearly eternal. Picture every nucleus in your body spontaneously disintegrating. Atoms falling apart without cause, matter dissolving into lighter particles. In our universe, protons are extraordinarily stable, with experiments at Kamioka Observatory setting their half-life at more than 10 to the 34th power years, trillions of times the age of the universe. This stability allows atoms to persist long enough for chemistry and life. But grand unified theories developed at Harvard in 2017 predict protons eventually decay into lighter particles. If a new Big Bang produced a universe where protons decay in seconds or years, no atoms could exist long-term. Stars would dissolve mid-formation, planets would evaporate, any chemistry would be fleeting. To think that the stability we take for granted, the persistence of matter from one moment to the next, could be a temporary feature of our specific physical laws. The Higgs field might have a different vacuum expectation value, making all particles massless. Consider that particles acquire mass by interacting with the Higgs field, a field that permeates all space, discovered at CERN in 2012. The strength of this interaction depends on the field's value in its lowest energy state, measured at 246 gigaelectronvolts. If a new Big Bang produced a universe where the Higgs field settled at zero, all particles would remain massless, like photons. Electrons would travel at light speed, unable to orbit nuclei or form atoms. Quarks would zip apart, unable to bind into protons. Research at the Large Hadron Collider in 2019 showed that the Higgs field's value determines the masses of all known particles. Without it, matter as we know it cannot exist. Only radiation and massless particles filling space. In a sense, mass itself is not inherent to particles but granted by their environment. Reality might be born without causality, where effects precede their causes. Imagine pressing a switch and watching the light turn on before your finger moves, or seeing a meteor impact before the meteor arrives. In our universe, causality flows from the structure of space-time and the second law of thermodynamics. But theoretical work by Yakia Aharonov at Tel Aviv University in 2016 explored quantum systems where future events influenced the past. If a new Big Bang produced space-time with a different topology, perhaps with closed time-like curves, causality could loop back on itself. Events could influence themselves, creating paradoxes or self-consistent loops. The universe might contain regions where time runs backward relative to others. To think that cause-following effect is not a logical necessity but a consequence of how space-time happens to be structured in our universe. Stars could form made entirely of dark matter, invisible and unknowable. Picture the night sky not as a scattering of visible stars, but as a hidden cosmos of gravitational wells, dark suns burning through processes we cannot observe. Research at Princeton in 2018 proposed that in dense regions of the early universe, dark matter particles could collapse under their own gravity to form dark stars. If these particles annihilate when they meet, as some theories suggest, energy would be released, potentially more power than fusion provides. A new Big Bang might produce conditions where dark matter dominates even more strongly, creating a parallel stellar population we could only detect through gravitational effects. Galaxies might consist of visible stars orbiting dark stars, an entire astronomical realm invisible to our telescopes. This reminds us that the universe we see might be a tiny fraction of what exists, most of reality hidden in darkness. The universe could emerge without space, only time. Consider navigating through a cosmos where distance has no meaning, where everything exists at the same location but in different moments. While this seems impossible, theoretical physicists at Oxford in 2019 explored spacetimes with only temporal dimensions. In such a universe, physical laws would be radically different. Events wouldn't spread through space, but unfold through time at a single point. No light could propagate, no forces could act at a distance, only sequential changes in state. Particles couldn't separate or come together, only transform. Research shows this configuration is mathematically consistent, but would bear no resemblance to our reality. In a sense, the three dimensions of space we navigate are not inevitable but one possibility among stranger alternatives. Particles might form but never settle into stable configurations. Imagine a universe where atoms exist for only microseconds before their electrons leap to different energy levels. where molecules form and break apart millions of times per second in eternal chaos. Research at the Niels Bohr Institute in 2017 showed that atomic stability depends on electrons finding discrete quantum states separated by energy gaps. If a new Big Bang produced different quantum numbers, or if the fine structure constant varied with time, these energy levels might constantly shift. Electrons would cascade up and down unpredictably, emitting and absorbing radiation in a frenzied dance. No chemistry could occur because bonds would break as fast as they formed. To think that the stillness of matter, the way atoms persist unchanged for billions of years, requires a quantum landscape that holds perfectly constant. The cosmic inflation period might never end, stretching space exponentially forever. Picture the first fraction of a second after the Big Bang, when space doubled in size every 10 to the negative 37th power seconds, but imagine it never stopping. In our universe, inflation lasted perhaps 10 to the negative 32nd power seconds before the inflaton field decayed into matter and radiation. Theoretical work by Andre Lind at Stanford in 2015 explored eternal inflation scenarios, where some regions keep inflating while others stop. If a new Big Bang triggered inflation that couldn't end, space would expand so rapidly that particles would be separated faster than light could travel between them. No structures could form because gravity would never overcome expansion. The universe would be empty space stretching forever, cold and structureless. This reminds us that the gentle expansion we observe required inflation to shut off at precisely the right moment. Magnetic monopoles might flood the universe, disrupting all electromagnetic processes. Consider that every magnet you've encountered has both north and south poles, inseparable pairs. But grand unified theories predict that isolated magnetic poles, monopoles, should have been created abundantly in the Big Bang. Experiments at the IceCube Neutrino Observatory in Antarctica through 2018 have searched for these particles without success. If a new Big Bang produced conditions where monopoles formed and didn't inflate away, they would radically alter electromagnetism. Research at the University of Chicago in 2016 calculated that monopoles would catalyze proton decay, destabilizing all matter. Their strong magnetic fields would disrupt atomic electron orbits and interfere with charged particle motion. The universe would be hostile to atoms and chemistry as we know them. In a sense, we exist in a universe mysteriously devoid of particles that theory says should be everywhere. Space-time could crystallize into a rigid lattice instead of remaining fluid. Imagine space itself solidifying like water freezing into ice, forming a grid of discrete points where continuous motion becomes impossible. Theoretical work on loop quantum gravity by Carlo Rovelli in 2018 suggests space-time might be quantized at the Planck scale, 10 to the negative 35th power meters. If a new Big Bang produced conditions where this quantum structure became macroscopic, space would have a definite grain. Particles couldn't move smoothly but would hop from point to point. Different directions might have different properties, breaking the isotropy of space. Calculations at the Perimeter Institute in 2019 showed that waves, including light, would behave strangely in crystalline spacetime, perhaps unable to propagate at all. To think that the smooth space we move through could instead be a frozen lattice where position is discrete. The weak nuclear force might not exist, preventing stars from burning. Picture a universe full of hydrogen that can never fuse because the process that converts protons to neutrons is forbidden. In our sun, nuclear fusion requires the weak force to change protons into neutrons through beta decay, releasing neutrinos in the process. This weak interaction mediated by W and Z bosons discovered at CERN in 1983, is essential for fusion to proceed. Research at Princeton Plasma Physics Laboratory in 2018 calculated that without the weak force, hydrogen fusion simply cannot occur because proton-proton reactions are blocked. Stars would never ignite, remaining cold clouds of gas. The universe would be dark and frozen, unable to produce the heavier elements formed in stellar cores. This reminds us that starlight depends not only on gravity and heat, but on one of nature's four fundamental forces, transforming matter. Every particle could have a different lifespan, creating matter that expires. Consider that in our universe, particles like electrons and quarks appear to be perfectly stable, lasting indefinitely. But research at the University of Washington in 2019 placed limits on electron stability, showing that if they decay at all, their half-life exceeds 10 to the 26th power years. If a new Big Bang produced a universe where particles had varied expiration dates, matter would be ephemeral. Atoms might persist for years or centuries before their constituent particles spontaneously transformed into other forms. Planets would gradually evaporate. Stars would fade not from fuel exhaustion, but from literal dissolution. Any life that emerged would face a universe where the substance of bodies and worlds slowly disappeared. In a sense, permanence of elementary particles is a gift, not a given, allowing structures to outlast the moments of their creation. Space could expand in some directions, but contract in others. Imagine east-west distances growing while north-south distances shrink. The universe stretching like taffy pulled in one direction while compressed in another. Our universe expands isotropically, meaning uniformly in all directions, confirmed by measurements of the cosmic microwave background by the Planck satellite in 2018, showing temperature variations of only 1 part in 100,000. But theoretical models explored at Cambridge in 2017 show that anisotropic expansion is possible if the Big Bang's initial conditions weren't perfectly symmetric. In such a universe, galaxies would be stretched into filaments. Space would have preferred directions, and the laws of physics might vary depending on which way you're facing. Light traveling in different directions would experience different redshifts. To think that the democracy of space, where all directions are equivalent, required an exceptionally symmetric beginning. Gravity might propagate instantly instead of at light speed. Picture the sun suddenly vanishing, and Earth immediately flying off its orbital path in the same instant, not 8 minutes later when the loss of sunlight reaches us. Einstein's general relativity, confirmed by LIGO's detection of gravitational waves in 2015, shows that changes in gravitational fields propagate at exactly the speed of light. But if a new Big Bang produced different space-time dynamics, this might not hold. Theoretical work at the University of Geneva in 2018 explored modified gravity theories where gravitational information travels faster or slower than light. If gravity propagated instantly, causality could be violated, effects could precede causes, and the stable orbital mechanics of planetary systems might become chaotic. If gravity traveled slower than light, the universe would look fundamentally different, with planets spiraling outward as they orbit. This reminds us that the speed limit of causality shapes the entire cosmic architecture. Quantum entanglement might not exist, isolating every particle. Consider that in our universe, particles can become entangled, sharing quantum states across vast distances, with measurements on one instantly affecting the other regardless of separation. Einstein called this spooky action at a distance, and experiments by Alling Aspect in 1982 and many since have confirmed it occurs. If a new Big Bang produced a universe without quantum entanglement, every particle would be truly independent. Research at the University of Vienna in 2019 showed that quantum computing, certain biological processes, and possibly the structure of space-time itself rely on entanglement. Without it, information would be strictly local. Quantum mechanics would be fundamentally simpler but less powerful, and the universe might be unable to maintain the complexity needed for consciousness. In a sense, the deep interconnectedness of quantum reality might be essential for minds to emerge. The universe could begin already filled with life-bearing worlds. Imagine a Big Bang that doesn't start from pure energy but somehow includes complex structures, planets already harboring organisms, civilizations beginning mid-conversation. While this violates our understanding of thermodynamics, theoretical work on the Boltzmann brain paradox by Sean Carroll at Caltech in 2017 explores whether random quantum fluctuations could produce organized systems. If a new Big Bang had extraordinarily low entropy in unusual ways, brief islands of complexity might emerge, fully formed, before dissolving. Calculations show this is fantastically improbable, but not impossible. Such a universe would age backward in a sense, structures decaying toward equilibrium rather than evolving from simplicity. To think that the arrow of time and evolution from simple to complex are not inevitable, but consequences of how our Big Bang began. All forces might unify permanently, creating a universe with only one interaction. Picture a cosmos where gravity, electromagnetism, and nuclear forces never separated into distinct phenomena, remaining merged as a single unified force. In our universe's first 10 to the negative 43rd power seconds, the Planck epoch, all forces were unified. As the universe cooled, they separated in stages. First gravity, then the strong force, finally electromagnetism and weak force, splitting at 10 to the negative 12th power seconds. Research at the University of Texas in 2018 modeled scenarios where cooling happens differently. If a new Big Bang produced a universe that never cooled enough for symmetry breaking, forces would remain unified. Particles would all behave identically under this single force. No distinction between electric charge and color charge and mass. Physics would be simpler, but probably unable to create complex structures. This reminds us that the rich diversity of interactions, enabling chemistry and life, emerged from symmetries breaking as temperature fell. Black holes might form spontaneously throughout space, without matter collapsing. Consider that in our universe, black holes form when massive stars collapse, or when dense regions of the early universe pinch off. But quantum field theory, developed by Stephen Hawking and others in the 1970s, shows that empty space seethes with vacuum energy. If a new Big Bang created spacetime with higher vacuum energy density, calculations from the University of Amsterdam in 2019 suggest quantum fluctuations could spontaneously create microscopic black holes. These would appear and evaporate through Hawking radiation in fractions of a second, filling the universe with a flickering foam of temporary black holes. Space would be turbulent and dangerous, with gravitational singularities popping into existence unpredictably. Stable structures like atoms or planets might be impossible because they'd be continually disrupted by these quantum black holes. In a sense, the calmness of space requires vacuum energy to be extraordinarily low. The arrow of time might point in opposite directions in different regions. Imagine traveling to a distant galaxy where eggs unbreak, where fires consume ashes and produce wood, where people are born old and die young as infants. The second law of thermodynamics states that entropy always increases, giving time its direction. But theoretical work by Sean Carroll in 2016 suggests the arrow of time is a consequence of the universe starting in an extraordinarily low entropy state at the Big Bang. If a new Big Bang produced a more random initial state, different regions might find themselves on opposite sides of the entropy curve. In some regions, entropy would increase into what we call the future. In others, entropy would increase in the opposite temporal direction. The laws of physics work equally well in both directions. To think that the past being fixed and the future open is not a law of nature, but a feature of where we sit on the entropy gradient. Particles might be unable to distinguish between types, making chemistry random. Picture atoms where electrons randomly become quarks, where photons transform into neutrinos without cause, where the identity of particles fluctuates from moment to moment. In our universe, conservation laws protect particle identity. Electrons remain electrons, quarks remain quarks. These conservation laws arise from symmetries, proven by Emmy Noether in 1915, to be deeply connected to the structure of space-time. If a new Big Bang produced different symmetries or none at all, particles might not have stable identities. Research at CERN in 2018 confirmed that particle types are determined by quantum numbers that are conserved in all observed interactions. Without these conservation laws, reactions would be unpredictable. Atoms couldn't exist in stable forms, and chemistry would be impossible because you couldn't rely on elements maintaining their properties. This reminds us that the periodic table depends on particles having permanent identities. The universe might be born with memories of events that never happened. Consider that in our universe, the past is recorded in present configurations. Fossils contain information about ancient life, and cosmic microwave background radiation preserves patterns from 380,000 years after the Big Bang. But research on cosmological initial conditions by Anthony Aguirre at UC Santa Cruz in 2017 explores whether a universe could begin with structure that appears to encode a history, even though no such history occurred. If a new Big Bang produced a complex initial state rather than near uniformity, that structure might look like remnants of previous events, false archaeological records written into the fabric of space. Observers in such a universe would find evidence of a past that never existed, stars that never burned, extinctions that never occurred. In a sense, this highlights that we infer the past from present evidence, and that evidence could theoretically be misleading if the universe began with complexity. Nuclear fusion might release less energy, making stars burn dim and cold. Imagine a sun that glows faintly, providing barely enough warmth for water to remain liquid on Earth, where photosynthesis struggles and life huddles near the equator. The energy released by fusion depends on the mass difference between reactants and products, related to Einstein's equation E equals mc squared. In our universe, when 4 hydrogen nuclei fuse to form helium, 0.7% of the mass converts to energy. Research at Lawrence Livermore National Laboratory in 2019 calculated that if this efficiency were even slightly lower, say 0.5%, stars would burn much dimmer and cooler. Their lifetimes would be longer, but their energy output lower, potentially too low to support life on planets in habitable zones. If fusion efficiency were higher, stars would burn hot and fast, living only millions of years instead of billions, too short for biological evolution. To think that life depends on fusion releasing precisely enough energy. All matter might be born rotating in the same direction, giving the universe angular momentum. Picture every galaxy, star, and planet spinning the same way, a cosmic carousel where nothing rotates backward. In our universe, galaxies spin in random directions, some clockwise, some counterclockwise from our perspective. This random orientation suggests the Big Bang itself had no net angular momentum. But theoretical work at Johns Hopkins University in 2018 explored scenarios where initial conditions could impart rotation. If a new Big Bang had angular momentum, all structures would inherit a preferred spin direction. Observations by the Sloan Digital Sky Survey through 2019 have checked for such patterns and found none, confirming our universe's Big Bang was not. A rotating universe would have different expansion rates in different directions, curved spacetime twisted into spiral patterns, and perhaps even closed, time-like curves enabling time travel. This reminds us that the universe could have been born spinning. The Pauli exclusion principle might not apply, causing all electrons to collapse into the lowest energy state. Consider that electrons are fermions, particles that cannot occupy the same quantum state as each other. This principle, discovered by Wolfgang Pauli in 1925, is why atoms have electron shells and why matter has volume. If a new Big Bang produced a universe without this rule, all electrons in an atom would fall into the ground state, the lowest energy level. Research at MIT in 2017 showed that without the exclusion principle, atoms would be vastly smaller, only the innermost shell would fill, and elements would be chemically identical. There would be no periodic table, no diverse chemistry, new complex molecules. Additionally, matter would collapse under gravity without limit, as electron degeneracy pressure, which prevents white dwarfs from collapsing, depends on the Pauli principle. In a sense, we are held apart not just by electromagnetic repulsion, but by a quantum rule about occupancy. Causality might operate only at quantum scales, making the macroscopic world random. Imagine dropping a cup and watching it sometimes fall, sometimes hover, sometimes fly upward, without rhyme or reason. In our universe, quantum uncertainty averages out for large objects, giving us deterministic classical physics. But theoretical work by Roger Penrose at Oxford in 2016 explored whether quantum effects might persist at larger scales under different conditions. If a new Big Bang produced weaker decoherence, the quantum fuzziness wouldn't average out. Large objects would exhibit superposition, cats might be genuinely both alive and dead, and the predictable world of everyday experience would dissolve into probability clouds. Measurements at the University of Vienna in 2018 showed that current experiments can maintain quantum superposition for objects containing thousands of atoms. To think that the solid, predictable nature of the everyday world depends on quantum effects being thoroughly hidden at large scales. Time might flow at different rates for different particle types. Picture electrons experiencing seconds while protons experience years, particles aging at different speeds even when side by side. In our universe, time dilation occurs due to velocity and gravity, but all particle types experience time identically in the same reference frame. But research on quantum gravity at the University of Waterloo in 2019 suggests time itself might be emergent from more fundamental quantum properties. If a new Big Bang produced different underlying structures, time might not be universal. Electrons might tick faster than quarks. Photons might experience no time at all as they do in our universe. But matter particles might also experience time differently from each other. Chemical reactions would become unpredictable because reactants would age at different rates. To think that the synchronization of time across all particles and all matter is not inevitable but a feature of how space-time is constructed. The cosmological horizon might be much smaller, making the observable universe tiny. Consider that in our universe, we can see galaxies up to 46 billion light-years away due to expansion. This horizon represents how far light has traveled in the 13.8 billion years since the Big Bang, stretched by expansion. If a new Big Bang produced faster expansion or occurred more recently, the horizon could be vastly smaller. Research at the University of Cambridge in 2017 calculated that if expansion were 10 times faster, our observable universe might extend only a few million light-years. We might see only our local galaxy group, or even just the Milky Way. Observers would have no knowledge of the vast cosmos beyond, believing their tiny bubble to be all that exists. This reminds us that what we can observe is limited not just by technology but by fundamental cosmological properties. And elsewhere might exist realms forever hidden from us. Nuclear decay rates might vary with location, making elements unstable in some regions. Imagine traveling to a distant galaxy where uranium decays in seconds instead of billions of years, where radioactive dating gives wildly different results. In our universe, decay rates are constant everywhere, a cornerstone of nuclear physics confirmed by experiments at the National Institute of Standards and Technology through 2019. But if a new Big Bang produced spatial variations in coupling constants, the forces governing decay would differ by region. Theoretical work at Imperial College London in 2018 explored such scenarios. Stars in high decay regions would have different nucleosynthesis, producing unusual elemental abundances. Planets might be radioactive death zones in some areas, temperate in others. Life could only emerge in stable regions, leading to a patchy universe of habitability. To think that the consistency of physical laws across space is a contingent fact, not a necessity. Quantum decoherence might never occur, preventing classical reality from emerging. Picture a world where every object remains in superposition forever, where measurement doesn't collapse wave functions, where nothing is ever definite. In our universe, interactions with the environment cause quantum systems to lose coherence and appear classical, a process studied extensively at Los Alamos National Laboratory since 2015. This decoherence happens so rapidly for large objects that we never see quantum effects in everyday life. If a new Big Bang produced weaker interaction between systems, or if the environment couldn't entangle with objects effectively, decoherence wouldn't occur. Research at UC Berkeley in 2019 showed that without decoherence, macroscopic objects would behave quantum mechanically. The universe would be a haze of possibilities, nothing definite, no single classical history. In a sense, the sharp, determined world we experience emerges from quantum mesenses, washing out through environmental interaction. Fundamental constants might drift randomly throughout space. Consider traveling through the cosmos and finding that, in one region, the speed of light is faster. In another, the gravitational constant is stronger. In another, Planck's constant has a different value. Our universe appears to have the same constants everywhere, tested by observing distant quasars whose light has traveled billions of years. Measurements by astronomers using the Very Large Telescope in Chile through 2018 found no variation in the fine structure constant across cosmic time and distance. But if a new Big Bang produced a universe with spatial randomness in these values, physics would be local, not universal. Stars would burn differently in different regions. chemistry would vary, and observers in separate parts of the universe would discover incompatible laws of nature. To think that science assumes universality, that discoveries here apply everywhere, an assumption that could be false in other cosmic configurations. The Planck length might be macroscopic, making space-time's graininess visible to the naked eye. Imagine looking at your hand and seeing that space itself is made of discrete chunks, tiny pixels of reality, each about a millimeter across, with gaps between them where nothing exists. In our universe, the Planck length is 10 to the negative 35th power meters, far too small to ever observe directly. This is the scale where quantum effects of gravity become important, explored theoretically by Max Planck in 1899. If a new Big Bang produced different fundamental constants, the Planck length could be much larger. Research at the Perimeter Institute in 2018 showed that if it reached even a micrometer, light would scatter off the granular structure of space. The sky would shimmer with diffraction patterns, and smooth motion would be impossible. Objects would jump from one space pixel to the next. To think that continuous space might be an illusion that holds only because the underlying grid is incomprehensibly fine. Antiparticles might live longer than particles, creating an antimatter-dominated cosmos. Picture a universe where positrons form stable atoms while electrons quickly decay, where antihydrogen builds stars while regular hydrogen vanishes. In our universe, particles and antiparticles have exactly equal lifetimes. Confirmed by experiments at CERN measuring antihydrogen in 2017 with precision 218 decimal places. This symmetry is called CPT invariance. But if a new Big Bang violated this symmetry, one type could outlast the other. Research published in Physical Review Letters in 2019 explored what such asymmetry would mean. If antiparticles were more stable, they would dominate the cosmos after matter decayed away. The chemistry would be identical since antimatter atoms behave exactly like matter atoms. But if any matter remained, annihilation reactions would make the universe violently energetic. This reminds us that we live in a universe that treats matter and antimatter nearly equally, and the slight difference determined which type survived. Consciousness might emerge instantly in the plasma of the first second. Consider that in our universe, consciousness required 13.8 billion years to emerge, needing stars to forge heavy elements, planets to form, life to evolve, brains to develop. But theoretical work on panpsychism by Philip Goff at Durham University in 2017 explores whether awareness might be a fundamental feature of matter itself. If a new Big Bang produced a universe where quantum information processing occurred in the primordial plasma, something like consciousness might exist immediately in the interactions of quarks and gluons. Research at the University of Arizona in 2018 investigated quantum theories of consciousness, suggesting awareness emerges from specific information patterns. The early universe, with its dense energy and rapid interactions, might briefly contain patterns complex enough for experience before cooling destroyed them. In a sense, the cosmos might have been briefly aware of its own birth before forgetting itself as it expanded. Space could have positive curvature, making the universe finite but unbounded. Imagine traveling in a straight line forever and eventually returning to your starting point, like walking around Earth's surface but in three-dimensional space. In our universe, measurements by the Planck satellite in 2018 show space is flat to within 0.4% accuracy, meaning parallel lines stay parallel forever. But if a new Big Bang produced slightly more density, space would curve back on itself like a sphere's surface. Research at Johns Hopkins University in 2016 calculated that a universe with positive curvature would be finite in volume, yet have no edge or boundary. Light could circumnavigate the universe, showing us multiple images of the same galaxy in different directions at different ages. If you looked far enough, you might see the back of your own head as it appeared billions of years ago. To think that infinity might not exist in physical space, that the universe could be both endless and limited simultaneously. Symmetry breaking might never occur, leaving all particles massless and identical. Picture the first moments after the Big Bang extending forever, the universe remaining a perfect democracy of identical particles with no distinctions, no hierarchy, no complexity. In our universe, as temperature dropped below 10 to the 15th power Kelvin at 10 to the negative 12th power seconds, the Higgs field underwent symmetry breaking, giving particles their individual masses. Before this moment, electrons, quarks, and neutrinos were indistinguishable. Research at the Large Hadron Collider through 2019 mapped this process precisely. If a new Big Bang somehow prevented cooling or the Higgs field settled at a different value, symmetry would remain unbroken. All particles would travel at light speed, unable to form atoms or any structure. The universe would be eternal radiation, photons and massless particles propagating forever without building anything. This reminds us that diversity, hierarchy, and structure emerged from a more perfect and symmetric state through what seems like cosmic imperfection. Quantum tunneling might occur at macroscopic scales, making solid objects permeable. Imagine placing a ball against a wall and watching it randomly appear on the other side without passing through. Not once in billions of years, but several times per minute. In our universe, quantum tunneling allows particles to pass through barriers they classically couldn't overcome, but the probability drops exponentially with object mass. Research at the University of California in 2017 showed that even a single atom tunneling through a barrier the width of a hydrogen atom has low probability. For larger objects, tunneling is so rare it never happens. But if a new Big Bang produced a universe with different quantum constants, specifically if Planck's constant were much larger, tunneling probability would increase dramatically. Calculations by physicists at MIT in 2018 showed that people might walk through walls occasionally. Objects would teleport unpredictably, and nothing could be contained reliably. To think that the solidity of barriers depends on Planck's constant being sufficiently small. The cosmic microwave background might be brighter than the sun, illuminating everything eternally. Consider that this ancient light currently has a temperature of 2.7 Kelvin, barely detectable without sensitive instruments. It's the cooled remnant of the fireball from 380,000 years after the Big Bang, stretched by expansion over 13.8 billion years. If a new Big Bang occurred more recently, or if expansion was slower, this background radiation would still be hot. Research at NASA's Goddard Space Flight Center in 2019 calculated that if the universe were only a few million years old with similar expansion, the background temperature might be thousands of Kelvin. The entire sky would glow bright orange or white. No darkness would exist anywhere, and any matter would be heated constantly by this omnipresent radiation. Stars would be invisible against the bright sky. Life would be impossible because nothing could radiate away heat. This reminds us that the cold darkness of space is not primordial but a consequence of age and expansion. Heavier elements might form directly without stars as intermediaries. Imagine a universe where carbon, oxygen, iron, and gold condensed directly from energy in the first minutes, where planets could form before the first star ignited. In our universe, Only hydrogen, helium, and traces of lithium formed in Big Bang nucleosynthesis during the first 3 minutes. All heavier elements required stars to forge them through fusion and supernova to scatter them. This process was mapped by Fred Hoyle and others in 1957. If a new Big Bang had higher density or lower expansion rate, conditions for fusion would persist longer. Calculations by cosmologists at the University of Tokyo in 2018 showed that with just 10 times the baryon density, fusion could produce elements up to iron directly. The universe would begin already enriched with heavy elements. Rocky planets might form in the first billion years, and perhaps life could emerge much earlier in cosmic history. To think that our need to wait billions of years for stellar nucleosynthesis might not be universal. Matter might repel matter while antimatter attracts antimatter, reversing gravity. Picture dropping an apple and watching it accelerate upward, while an anti-apple would fall down normally. In our universe, gravity is always attractive for all forms of mass and energy, positive or negative charge, matter or antimatter. This was confirmed by experiments at CERN in 2018, showing antihydrogen falls downward, just like regular hydrogen. But if a new Big Bang produced different gravitational properties tied to particle type, matter might gravitationally repel itself. Research at the University of California in 2017 explored such scenarios. Theoretically, in a matter-repulsive universe, gas clouds couldn't collapse to form stars. Matter would disperse uniformly, but antimatter would still clump. If any antimatter remained after annihilation, it alone would form structures, creating antimatter galaxies held together while matter filled the voids between them. In a sense, gravity being universally attractive is not logically necessary but empirically true for our universe. Black holes might evaporate faster than they form, preventing permanent event horizons. Consider that Hawking radiation causes black holes to lose mass over time, with smaller holes evaporating faster. In our universe, a black hole with the mass of the Sun would take 10 to the 67th power years to evaporate, far longer than the universe's current age. But Stephen Hawking's 1974 calculations show evaporation rate depends on fundamental constants. If a new Big Bang produced a universe with stronger Hawking radiation, perhaps through different gravitational coupling, even massive black holes might evaporate in seconds. Research at the University of Cambridge in 2019 explored these scenarios. Black holes would be transient flashes rather than permanent cosmic features. Matter falling toward a singularity would be radiated away before the event horizon fully formed, and the universe would lack these ultimate gravitational prisons. To think that black holes might be temporary features specific to universes where Hawking radiation is weak, like ours. The cosmological constant could vary with time, making expansion accelerate, then decelerate. Imagine living in a universe where distant galaxies rush away faster each billion years, then suddenly the expansion slows, stops, and reverses. In our universe, dark energy appears constant with time, driving steady, accelerating expansion measured by observations of distant supernova since 1998. But research by the Dark Energy Survey through 2019 allows for the possibility that dark energy's strength changes. If a new Big Bang produced a time-varying cosmological constant, cosmic evolution would be far more dynamic. Theoretical work at Princeton in 2018 showed that if dark energy weakened with time, the universe might eventually recollapse in a big crunch. If it strengthened, acceleration would intensify until space tears apart in a big rip. The fate of the cosmos would be uncertain, dependent on how this fundamental property evolves. This reminds us that the universe's future depends on properties we're still measuring, and other universes might have different destinies. Photons might decay into other particles, making light temporary. Picture sunlight that fades to nothing halfway to Earth, where distant stars are invisible not because they're far, but because their light dissolves in transit. In our universe, photons are stable, traveling unchanged for billions of years across cosmic distances. This stability is protected by conservation of energy and charge. But theoretical extensions to the Standard Model explored at the University of Geneva in 2017 suggest photons might very slowly decay into hypothetical particles like ixions under certain conditions. If a new Big Bang produced a universe where photon decay was rapid, vision would have limited range. Stars would be invisible beyond a few light years. Photosynthesis would be impossible, and electromagnetic radiation couldn't carry information across space. Astronomers at the Max Planck Institute in 2018 set limits on photon decay by observing light from distant galaxies, confirming it's extraordinarily rare if it happens at all. In a sense, transparent space depends on light's refusal to transform during its journey. The universe might be born with pre-existing black holes of all sizes. Consider that in our universe, black holes form from gravitational collapse of massive stars or from dense regions in the early universe. But primordial black holes, formed in the first, second, are theoretically possible from density fluctuations. If a new Big Bang produced larger initial density variations, research by Juan Garcia Bellido at Madrid Autonomous University in 2018 shows black holes of any mass could form immediately. The universe might begin already dotted with black holes ranging from microscopic to galactic scale, their gravity shaping structure before stars ever formed. Tiny primordial black holes might even constitute dark matter. Galaxy formation would be accelerated, matter pulled into existing gravitational wells. The cosmic landscape would be determined from the first instant, leaving less room for chance and evolution. To think that structure might be imprinted at creation rather than emerging gradually through gravitational collapse. Quantum measurement might collapse all entangled particles simultaneously, everywhere. Imagine observing an electron's spin here and instantly causing every entangled particle across the entire universe to snap into definite states, a cascade of measurement collapsing wave functions in distant galaxies. In our universe, measuring an entangled particle affects its partner instantly, but this doesn't propagate beyond the entangled pair. Research by Anton Zeilinger at the University of Vienna through 2019 has tested entanglement over hundreds of kilometers. But if a new Big Bang produced a universe with stronger or more pervasive entanglement, measurement might cascade. Theoretical work at the Institute for Advanced Study in 2017 explored whether universal entanglement could create a cosmos-wide quantum state. A single observation might affect the entire universe simultaneously, collapsing superpositions everywhere. The act of measurement would have cosmic significance. Observers would shape distant reality by observing locally. This reminds us that the quantum boundary between observer and observed might be drawn differently under alternative physical laws. Nuclear fusion might occur at room temperature, making matter violently unstable. Picture hydrogen gas spontaneously igniting into helium without compression or heat. Water molecules fusing their hydrogen nuclei into heavier elements unpredictably, your body converting to pure energy randomly. In our universe, fusion requires temperatures of millions of Kelvin because atomic nuclei must overcome electromagnetic repulsion to get close enough for the strong force to bind them. Research at the National Ignition Facility through 2018 shows achieving fusion requires extraordinary conditions. But if a new Big Bang produced weaker electromagnetic force or stronger strong force, the barrier to fusion would be lower. Calculations at Los Alamos in 2019 showed that with electromagnetic force just 10 times weaker, fusion could occur at ordinary temperatures. Matter would be explosive, hydrogen couldn't exist stably, and the universe would quickly convert to iron and radiation. To think that matter's stability depends on fusion being difficult, requiring stellar furnaces rather than occurring spontaneously. Entropy might decrease naturally, causing broken systems to spontaneously repair. Imagine shattered glass reassembling itself, dispersed perfume molecules gathering back into a bottle, aging creatures growing younger as cells organize rather than deteriorate. The second law of thermodynamics, verified in countless experiments since the 1850s, states that isolated systems become more disordered over time. But research by Lorenzo McCone at MIT in 2009 explored whether the arrow of time could point both ways. If a new Big Bang produced initial conditions at maximum entropy rather than minimum, the only direction for entropy to go would be down. The universe would progress toward order, complexity emerging not despite entropy but because of it. Research at the University of Maryland in 2018 showed such a universe would violate our intuitions about cause and effect, with consequences preceding their causes from our perspective. In a sense, death and decay are not inevitable but specific to universes like ours that started in exceptionally low entropy states. Space-time might have holes or disconnected regions impossible to reach. Consider traveling through space and encountering a boundary beyond which nothing exists, not even emptiness, just a void where space-time itself ends. In our universe, space appears continuous and connected everywhere, able to be traversed, given sufficient time. But topological defects explored, theoretically, by Alexander Vilenkin at Tufts University in 2016 suggests spacetime might contain boundaries or disconnected regions. If a new Big Bang produced such a universe, some galaxies might be causally isolated, existing in separate spatial bubbles with no path connecting them. Light couldn't travel between these regions, not because distance is too great, but because the space linking them doesn't exist. Research at the University of Oxford in 2019 showed that observers in one bubble would be forever unaware of other bubbles, each isolated cosmos believing itself to be the entire universe. To think that beyond our observable universe might exist not just distant regions, but fundamentally separate realities. Every particle might have a different charge value, making electromagnetism chaotic. Picture atoms where each electron carries a unique charge, some strongly negative, others barely charged at all. Protons similarly varied. In our universe, every electron has exactly the same charge, negative 1.602 times 10 to the negative 19th power coulombs, and every proton has exactly the opposite, positive charge. This uniformity is fundamental to chemistry and the stability of matter. Research at the University of Washington in 2018 measured electron charge to extreme precision, finding no variation. But if a new Big Bang assigned charges randomly to particles, atoms couldn't be neutral. Chemical bonding would be unpredictable, and molecules would tear apart or clump erratically. Calculations at Caltech in 2019 showed that even 1% variation in electron charges would make stable chemistry impossible. The periodic table would collapse into chaos. In a sense, the universe's reproducibility depends on identical particles being truly identical. The cosmic expansion might happen in quantum jumps, rather than smoothly. Imagine space expanding in sudden discrete bursts, galaxies leaping away in jerks, separated by pauses, the universe stuttering rather than flowing. In our universe, expansion appears continuous, measured by redshift of distant galaxies, showing smooth motion. The Hubble Space Telescope confirmed this through observations published in 2019. But if a new Big Bang produced a universe where expansion is quantized, space would grow in minimum increments, like climbing a staircase. Theoretical work on quantum cosmology at Penn State University in 2017 explored such scenarios. During pauses, galaxies would remain fixed, then suddenly jump farther apart. Light would experience discontinuous redshift. The concept of continuous time and space would break down at cosmological scales. To think that smooth expansion is not inevitable but could be replaced by a jerky, quantized growth, where the universe evolves in discrete steps. Causality loops might exist naturally, allowing events to influence their own past. Picture a particle that travels through time to collide with itself earlier, creating the conditions for its own creation. A self-causing event with no external origin. In our universe, causality flows forward. Effects follow causes, and time travel appears impossible according to general relativity under normal conditions. But research by Kip Thorne at Caltech in the 1980s showed that certain space-time configurations, like wormholes or rotating black holes, might permit closed time-like curves where time loops back. If a new Big Bang produced a universe with such geometry built in, perhaps with inherent space-time twists, causality loops might be common. Work at the University of Queensland in 2018 explored consistency conditions for such loops. Events would need to be self-consistent, preventing paradoxes but allowing strange causal structures. To think that cause and effect might weave in loops rather than chains, with some events being their own ancestors. The fine structure constant might vary across the electromagnetic spectrum, making different colors of light follow different rules. Imagine red light bending more strongly through glass than blue light does, but then experiencing weaker attraction to electrons, while violet light might move slower than radio waves in vacuum. In our universe, the fine structure constant, approximately 1 divided by 137, governs all electromagnetic interactions identically regardless of photon energy. Measurements by Paul Dirac in 1937 and refined experiments at NIS through 2019 confirmed this constancy across all wavelengths. But if a new Big Bang produced energy-dependent electromagnetic coupling, each frequency would interact differently with matter. Research at the University of New South Wales in 2018 explored such scenarios. Atoms would absorb and emit different colors with varying probabilities. Stellar spectra would be unrecognizable, and chemistry would depend on what color light illuminates molecules. Vision would be impossible because different wavelengths would scatter unpredictably from surfaces. To think that color uniformity in physical law makes the visible world comprehensible. Quantum superposition might collapse only after a fixed time delay, not upon measurement. Picture observing Schrödinger's cat and seeing it in a blur of both alive and dead for exactly 10 seconds before it suddenly resolves to one state. In our universe, measurement appears to collapse superposition instantaneously, though the exact mechanism remains debated. Experiments at the University of Vienna in 2019 using molecules showed collapse happens faster than current instruments can measure. But if a new Big Bang produced a universe with delayed collapse, observations would take time to become definite. Research at Chapman University in 2017 explored modified quantum mechanics with collapse delay. Observers would see quantum fuzziness persist briefly before sharpening into classical reality. Multiple observers might see different outcomes during the delay period until consensus emerged. The boundary between quantum and classical would become a temporal transition zone rather than an instant. In a sense, reality might need time to decide what happened. Every galaxy might orbit a common center, making the universe rotate as a whole. Consider that in our universe, galaxies move away from each other in all directions due to expansion, with no preferred center or axis. Observations by Edwin Hubble in 1929 established this, refined by surveys through 2019 showing isotropic expansion. But if a new Big Bang imparted angular momentum to the entire cosmos, the universe would spin like a vast carousel. Research by Michael Longo at the University of Michigan in 2011 analyzed spiral galaxy orientations, finding them randomly distributed, confirming no universal rotation. If rotation existed, space-time would be twisted, Coriolis forces would affect cosmic structure formation, and light traveling parallel to the rotation axis would be redshifted differently than light traveling perpendicular. Distant galaxies would appear to move in curved paths rather than straight radial motion. To think that cosmic stillness, the lack of universal spin, required initial conditions with zero net angular momentum. Particles might exist in multiple locations simultaneously without superposition. Imagine an electron literally being in two places at once, not as a probability wave but as genuine simultaneous existence, occupying separate positions, definitely. In our universe, particles in superposition aren't in multiple places but exist in an indefinite state until measured. Quantum mechanics, formulated in the 1920s, describes this mathematically as wave functions. But theoretical work on non-local hidden variable theories by physicists at Bristol University in 2018 explored whether particles might genuinely multilocate. If a new Big Bang produced such physics, one particle could participate in multiple reactions simultaneously in distant locations. Conservation laws would become strange, counting one particle in multiple places. Chemical bonds might form between atoms separated by vast distances if their electrons literally shared positions. To think that singularity of location, the assumption that something is in one place at one time, might not be mandatory for particles. The holographic principle might operate in reverse, with 3D information encoded on 2D surfaces. Consider that theoretical work by Gerard T. Hooft in 1993 and Leonard Susskind in 1995 suggests our three-dimensional universe might be a hologram projected from information on a two-dimensional boundary. Mathematical studies of black holes show they store information on their event horizon surface, not throughout their volume. If a new Big Bang produced a universe where this relationship reversed, three-dimensional regions would encode information about higher dimensional spaces. Research at the Institute for Advanced Study in 2019 explored such scenarios. We might be living in a projection of a 4 or 5-dimensional reality, our perceived depth an illusion created by information compressed in our 3D space. Physics might be simpler when described in the higher dimension, with our complicated laws emerging from projection. This reminds us that the dimensionality we experience might not be the fundamental arena where physics truly operates. Neutrinos might be their own antiparticles, causing them to annihilate themselves randomly. Imagine particles that occasionally encounter themselves in their own internal quantum state and vanish in a flash of energy without meeting another particle. In our universe, it remains unknown whether neutrinos are Majorana particles. identical to their antiparticles or Dirac particles, distinct from them. Experiments at the Sudbury Neutrino Observatory through 2018 haven't yet resolved this question. If a new Big Bang produced Majorana neutrinos with strong self-interaction, these ghostly particles would randomly annihilate themselves. Research at Yale in 2019 calculated that this would make neutrinos far less abundant, removing them as significant contributors to cosmic mass. The fusion processes in stars that produce neutrinos would be affected, potentially making stellar evolution unpredictable as neutrino pressure would fluctuate. To think that particles might be their own opposites, capable of self-destruction without external interaction. Gravity might have a maximum range beyond which it simply stops operating. Picture our solar system held together by the sun's gravity, but galaxies beyond a certain distance feeling no gravitational attraction from each other at all, not weakened but absent. In our universe, gravity's strength decreases with distance but never reaches zero, falling off as the inverse square of separation. Newton formulated this in 1687, and Einstein's general relativity confirmed gravity operates across any distance. But if a new Big Bang produced a massive graviton, the hypothetical particle carrying gravitational force, gravity would have limited range like the weak nuclear force does. Research at the University of Washington in 2018 set experimental limits, showing that if gravity has a cutoff, it must be beyond millions of light years. In such a universe, distant galaxy clusters would be causally disconnected gravitationally, cosmic structure would form only locally, and the large-scale universe would be fragmented into isolated gravitational domains. In a sense, cosmic unity depends on gravity's infinite reach. The Higgs boson might be unstable, causing mass to fluctuate randomly. Consider that the Higgs field gives particles their mass through interaction, discovered at CERN in 2012. The Higgs boson itself, the quantum of this field, appears stable in our universe. But theoretical calculations by Joseph Likon at Fermilab in 2013 suggest the Higgs might be metastable, existing in a false vacuum that could decay. If a new Big Bang produced an unstable Higgs boson that decayed frequently, the Higgs field would fluctuate in strength. Research published in Physical Review D in 2019 explored consequences. Particle masses would vary randomly over time and space, electrons becoming heavier than lighter unpredictably. Atoms would constantly change size, chemical bonds would break and reform chaotically, and no stable matter could exist. The universe would shimmer with particles gaining and losing mass in quantum fluctuations amplified to macroscopic scales. To think that mass constancy, the unchanging weight of matter, depends on the Higgs field maintaining a steady value. Dark energy might clump into massive structures instead of spreading uniformly. Imagine regions of space where dark energy concentrates, creating zones of ultra-rapid expansion surrounded by calmer areas where galaxies can form normally. In our universe, dark energy appears perfectly uniform, a cosmological constant distributed equally throughout space. Observations by the Dark Energy Survey through 2018 found no evidence of clustering or variation. But if a new Big Bang allowed dark energy to behave like matter, able to clump gravitationally, the cosmos would be wildly not uniform. Research at the University of Pennsylvania in 2017 modeled such scenarios. Dark energy voids would contain galaxies and structure, while dark energy concentrations would be sterile expanses where space itself inflates violently. The universe would resemble foam, with pockets of structure separated by inflating bubbles. Observers in different regions would measure dramatically different expansion rates and cosmic properties. This reminds us that dark energy's smoothness creates the large-scale uniformity we observe. Atomic nuclei might oscillate in size, expanding and contracting rhythmically. Picture the nucleus of every atom pulsing like a beating heart, growing larger and shrinking thousands of times per second, protons and neutrons dancing in and out. In our universe, nuclei maintain constant size determined by the balance between strong nuclear attraction and electromagnetic repulsion among protons. Measurements at MIT in 2019 using electron scattering show proton radius of 0.84 femtometers, stable and unchanging. But if a new Big Bang produced time-varying coupling constants for nuclear forces, this balance would shift periodically. Research at the University of Manchester in 2018 explored oscillating fundamental constants. Nuclear binding energy would fluctuate, some moments releasing energy, others absorbing it. Atoms would emit and absorb radiation in complex patterns unrelated to electronic transitions. Chemistry would become temporally dependent, reactions proceeding at certain phases of the nuclear oscillation but not others. To think that nuclear stability, the unchanging heart of atoms, could instead be a dynamic rhythm. Magnetic fields might exist without electric currents creating them. Consider that in our universe, magnetism is generated by moving electric charges, by current flowing through wires, or by spinning electrons in atoms. Maxwell's equations, formulated in 1865, describe this relationship precisely. Experiments at the National High Magnetic Field Laboratory through 2019 confirm all observed magnetic fields trace to charge motion. But if a new Big Bang produced fundamental magnetic charge, monopoles that generate magnetic fields inherently, magnetism would be independent. Research at the University of Tokyo in 2017 explored physics with abundant monopoles. Magnetic fields would permeate space naturally without requiring currents. Electromagnetic induction would work differently, and the familiar relationship between electricity and magnetism would be altered. Electronic devices would be impossible as we know them, but entirely new technologies based on magnetic charge might exist. In a sense, the asymmetry between electricity and magnetism, where electric charge exists freely but magnetic charge apparently doesn't, shapes our technological civilization. Vacuum fluctuations might be large enough to create and destroy stars spontaneously. Imagine looking at empty space and watching a star blink into existence from nothing, shine for a few seconds, then dissolve back into vacuum. In our universe, quantum field theory predicts vacuum energy fluctuations, but they're extraordinarily small, creating virtual particle pairs that exist for fleeting moments at subatomic scales. Measurements of the Casimir effect by Steve Lamero in 1997 confirmed these fluctuations exist. But if a new Big Bang produced a universe with vastly higher vacuum energy, fluctuations would be proportionally larger. Calculations at the University of Amsterdam in 2018 showed that if vacuum energy were 10 to the 60th power times larger, fluctuations could momentarily create macroscopic objects. Space would be violent and chaotic, matter appearing and vanishing constantly, making stable structures impossible. To think that the calmness of empty space, its refusal to spontaneously generate large objects, requires vacuum energy to be extraordinarily small. Quantum entanglement might fade with distance, making locality emerge naturally. Picture two entangled particles that correlate perfectly when close, but gradually become independent as they separate, their connection weakening like a stretched rubber band. In our universe, entanglement appears distance independent. tested by experiments over hundreds of kilometers and potentially across cosmic distances. Anton Zeilinger's research through 2019 found no decay in entanglement strength with separation. But if a new Big Bang produced a universe with distance-dependent quantum correlations, locality would emerge naturally at large scales. Theoretical work at the University of Waterloo in 2018 explored such modifications. Nearby particles would exhibit strong quantum correlations, but distant particles would behave classically and independently. This would resolve the tension between quantum non-locality and relativity's speed of light limit, making the universe more intuitive at large scales while preserving quantum weirdness locally. In a sense, this would make quantum mechanics a local theory naturally. The cosmological constant might be negative, causing the universe to collapse immediately. Consider that dark energy in our universe has positive value, driving acceleration. Measurements show it constitutes about 68% of cosmic energy density, with a value around 10 to the negative 52nd power per square meter. But Einstein's equations allow negative cosmological constant, which would create attractive force strengthening with distance. If a new Big Bang produced negative dark energy, research at Cambridge University in 2017 calculated the universe would recollapse in seconds or years, depending on magnitude. Expansion from the Big Bang would slow, stop, then reverse. All matter would fall back together in a big crunch, heating to primordial temperatures. The universe's lifetime would be measured in moments, far too brief for stars, planets, or any complexity. To think that cosmic longevity depends on dark energy having positive sign, pushing outward rather than pulling inward. Planck's constant might be infinite, making quantum effects dominate at all scales. Imagine everyday objects exhibiting interference patterns, cars tunneling through garage walls, people existing in superposition across entire cities until observed. In our universe, Planck's constant equals 6.6 to 6 times 10 to the negative 34th power joule-seconds, small enough that quantum effects vanish for objects larger than molecules. Research at the University of Vienna in 2019 pushed quantum interference to objects of 2,000 atomic mass units, still microscopic. But if a new Big Bang produced infinite or vastly larger Planck's constant, quantum mechanics would govern everything. Calculations at MIT in 2018 showed that macroscopic objects would have quantum wavelengths meters long, exhibiting wave behavior and uncertainty. Determinism would vanish at all scales. The classical world wouldn't exist, and predicting anything would be impossible. To think that the solid, predictable, macroscopic world exists only because quantum fuzziness is confined to the very small by Planck's constant being tiny. Every particle might leave a permanent record in spacetime, making the past directly observable. Picture looking at empty space and seeing ghostly trails showing every particle that ever passed through. A historical record written into the fabric of reality itself. In our universe, particles move through spacetime, leaving no permanent mark. Information about past states preserved only in current configurations through causal chains. But research on quantum information at the University of Maryland in 2018 explores whether information could be indelibly encoded in space-time structure. If a new Big Bang produced a universe where particle trajectories permanently altered space-time topology, the past would remain visible. Observers with the right instruments could see directly what happened billions of years ago, not by detecting ancient light, but by reading the structure of space itself. History would be non-erasable. every event preserved forever. This reminds us that in our universe, the past is lost except for traces that survive in present structures. The speed of causality might vary by direction, making time flow faster toward certain regions. Imagine traveling north and experiencing days passing in seconds, while moving south slows time to a crawl, with different directions in space having different temporal velocities. In our universe, the speed of light and causality is the same in all directions, tested precisely by the Michelson-Morley experiment in 1887 and confirmed by countless measurements since. Research at NIST through 2019 verified isotropy to within 1 part in 10 to the 17th power. But if a new Big Bang produced anisotropic spacetime, perhaps from initial conditions with preferred directions, causality would propagate differently along different axes. Theoretical work at Stockholm University in 2018 explored such universes. Light would travel at different speeds depending on direction. Stellar positions would shift based on viewing angle, and observers moving different directions would age at different rates, even at the same velocity. To think that the equality of all directions in space, the absence of cosmic orientation, required extraordinarily symmetric initial conditions. Quantum wave function collapse might release energy instead of being passive. Picture every measurement creating a burst of radiation, every observation lighting up the universe, consciousness itself generating power. In our universe, wave function collapse appears to be an informational event without direct energy cost, though the mechanism remains mysterious. Experiments at the University of Queensland through 2019 found no energy release during quantum measurements. But if a new Big Bang produced a universe where collapse converts probability into energy, measurements would be thermodynamic events. Research at the University of Innsbruck in 2017 explored energetic collapse models. Every observation would heat the universe slightly. Matter would glow from constant quantum measurements by its environment, and the act of awareness might be detectable through energy signatures. The universe would slowly heat from accumulated collapse energy, and life itself would contribute to cosmic warming through its observations. In a sense, observation would be an active force rather than passive reception. Neutron stars might be unable to form, leaving only black holes or complete dispersion after supernova. Consider that in our universe, when massive stars explode, cores between about 1.4 and 3 solar masses compress into neutron stars, incredibly dense objects held up by neutron degeneracy pressure. Research at the Max Planck Institute in 2018 mapped this process precisely. But if a new Big Bang produced a universe with slightly stronger gravity or weaker strong nuclear force, neutron degeneracy wouldn't be sufficient to halt collapse. Calculations at Caltech in 2019 showed that stellar cores would either blow apart completely or plunge through the neutron star phase directly into black holes. No pulsars would exist, no neutron star mergers to create heavy elements through our process nucleosynthesis, and gold, platinum, and uranium would be cosmically rare or absent. The universe would be divided between black holes and dispersed gas, missing the intermediate state that creates much of the periodic table. To think that neutron stars exist only in a narrow range of possible physical laws. Time dilation might be reversed, with moving clocks running faster instead of slower. Imagine astronauts returning from high-speed journeys older than those who stayed home, time accelerating rather than slowing with velocity. In our universe, special relativity predicts and experiments confirm that moving clocks run slower, proven by atomic clocks aboard aircraft and GPS satellites. Research at NIST in 2010 measured time dilation with clocks differing in speed by just meters per second. But if a new Big Bang produced space-time with opposite metric signature, the relationship would invert. Theoretical work at the University of Vienna in 2017 explored negative metric signatures. Faster objects would experience more time, making acceleration, a time machine to the future, impossible, but enabling the opposite effect. Causality would be preserved but profoundly altered, and the universe's global structure would differ dramatically. To think that time slowing with motion is not logically necessary but a consequence of spacetime's particular mathematical structure. Every quantum measurement might create a permanent new timeline that coexists with the original. Picture each observation splitting reality into branches where all possible outcomes occur. Not metaphorically, but as actual physical universes proliferating with each quantum event. This is the many worlds interpretation proposed by Hugh Everett in 1957, which treats wave function collapse as illusion, all possibilities realized in parallel. Research at Oxford by David Deutsch through 2019 has developed this mathematically. If a new Big Bang produced a universe where branches are more distinct or detectable, observers might perceive evidence of parallel timelines. Quantum computers might communicate with their parallel counterparts, and the universe would be an ever-branching tree of realities, with your consciousness following just one path through infinite possibilities. The universe's complexity would be inconceivable. Every quantum event since the Big Bang creating exponentially multiplying worlds. In a sense, reality might be vastly larger than the single timeline we perceive. Atomic orbitals might be physical shells rather than probability clouds. Imagine electrons confined to actual spherical surfaces around nuclei, orbiting on definite tracks like planets around a star. In our universe, quantum mechanics describes electrons as probability distributions, cloud-like regions where the particle might be found. Experiments from the 1920s onward confirmed this probabilistic nature. But if a new Big Bang produced a universe with hidden variables that define exact particle positions, as proposed by David Bohm in 1952, electrons might follow deterministic paths through their probability clouds. Research at Utrecht University in 2018 explored Bohmian mechanics. Particles would have definite positions always, guided by quantum wave functions, and the uncertainty principle would reflect ignorance rather than fundamental randomness. Chemistry would look identical macroscopically, but operate deterministically at the quantum level. To think that quantum randomness might be apparent rather than real, particles following hidden choreography we cannot observe. The early universe might have produced primordial life in the plasma before atoms formed. Consider that in our universe, life required planets, liquid water, and complex chemistry that took billions of years to develop. But research by Paul Davies at Arizona State University in 2010 explored whether information processing patterns might exist in the quark-gluon plasma of the first microsecond. If a new Big Bang produced a universe where the early plasma had regions of different properties that could interact, something analogous to metabolism might occur. Calculations at the University of Columbia in 2019 showed that if the plasma persisted longer, lasting minutes instead of microseconds, complex interacting patterns might emerge before nucleosynthesis destroyed them. These patterns would be completely unlike modern life, existing in conditions billions of times hotter than the sun's core, but they would process information and replicate patterns. To think that consciousness might have briefly existed in the universe's first moments, then vanished forever as temperature dropped. Gauge symmetries might be visible rather than hidden, making force carriers observable as structures. Imagine seeing the photons that create electromagnetic forces as glowing threads connecting charged particles. Gluons visible as colorful bonds between quarks. A universe where abstract mathematical symmetries have tangible form. In our universe, gauge bosons like photons and gluons are the force carriers but aren't directly visible. Only their effects manifest. Research at CERN through 2019 studies these particles in high-energy collisions. But if a new Big Bang produced a universe where gauge fields had additional properties, perhaps coupling to another field, they might leave visible traces. Theoretical work at Princeton in 2018 explored such extensions. Space would shimmer with force fields, electromagnetic bonds between atoms would glow, and the abstract machinery of quantum field theory would be observable phenomena. Physics would be more intuitive because the causes of forces would be visually apparent. In a sense, we live in a universe where the deepest truths are invisible. Quantum decoherence might be reversible, allowing classical objects to return to superposition. Picture a cup that falls, breaks, then through careful manipulation is restored, not just physically but quantum mechanically, to a superposed state of intact and broken simultaneously. In our universe, decoherence is effectively irreversible. The quantum information spreading into the environment so thoroughly that reconstruction is impossible. Research at the University of California, Santa Barbara in 2019 showed that even for simple systems, reversing decoherence requires controlling every environmental degree of freedom. But if a new Big Bang produced a universe with less chaotic dynamics or lower entropy increase, decoherence might be undone. Calculations at MIT in 2017 explored such scenarios. Macroscopic quantum effects could be restored, time might be more reversible, and the boundary between quantum and classical would be permeable in both directions. Objects could shift between definite and indefinite states through controlled processes. To think that the one-way nature of decoherence, classical certainty emerging from quantum fuzziness, might not be absolute. Dark matter might interact with itself strongly, forming dark matter atoms and molecules. Consider that in our universe, dark matter appears to interact only gravitationally, passing through itself and ordinary matter without friction or structure. Observations of colliding galaxy clusters like the Bullet cluster in 2006 showed dark matter behaving like a collisionless gas. But if a new Big Bang produced dark matter with self-interactions, research at UC Riverside in 2018 showed it could form complex structures. Dark matter would clump more efficiently, potentially forming dark atoms with dark nuclei and dark electrons, bound by dark electromagnetism. Dark chemistry might occur, dark planets might orbit dark stars, and an entire shadow universe of structure could exist interpenetrating our own, invisible but gravitationally present. Dark life might even emerge on dark worlds. To think that the simplicity of dark matter, its apparent lack of structure, might not be universal, and parallel complexity might exist in sectors we cannot observe. Every particle might experience a unique personal time, with no universal clock. Imagine asking what time it is and realizing the electron experiences different durations than the proton beside it, each particle aging at its own rate unrelated to others. In our universe, time is a shared dimension. All particles in the same reference frame experience the same temporal flow. This universality underlies physics, allowing us to define simultaneity locally. But research on quantum gravity at the University of Nottingham in 2019 suggests time might be emergent from more fundamental, timeless quantum states. If a new Big Bang produced a universe where time emergence was incomplete or varied by particle type, each particle would have intrinsic temporal properties. Theoretical work at the Institute for Quantum Optics in 2018 explored such models. Synchronization would be impossible, causality would be ambiguous, and describing dynamics would require tracking individual particle times rather than universal time. To think that the common flow of time, allowing us to say now, might be a special case rather than a necessity. The cosmological principle might be false, with dramatically different physics in different cosmic regions. Picture traveling 1 billion light-years and discovering that stars there burn blue, regardless of size. That gravity is weaker, that chemistry produces elements in reverse order from our region. In our universe, the cosmological principle states that the universe is homogeneous and isotropic at large scales, the same everywhere. Observations of the cosmic microwave background and large-scale structure through 2019 confirm this. But if a new Big Bang produced a universe with varying initial conditions, different domains might have different vacuum states and constants. Research at the University of Helsinki in 2017 explored bubble universes where regions underwent different symmetry breaking. Observers in different zones would discover incompatible laws of nature, making cosmology local rather than universal. Science itself would be geography-dependent, truths here being falsehoods there. In a sense, physical law, being universal, is contingent on cosmic homogeneity. Gravity might create, rather than curve space-time, generating new dimensions continuously. Consider that in our universe, Einstein's general relativity describes gravity as curvature of existing space-time, mass bending the four-dimensional fabric. But if a new Big Bang produced dynamics where gravitational energy births new spatial dimensions, the universe would grow not just in size but in dimensionality. Research at the Kavli Institute in 2018 explored such generative models. As matter accumulated, additional dimensions would unfurl around massive objects, making space near stars four-dimensional, near galaxies five-dimensional. Particles would move through more degrees of freedom in strong gravitational fields, leading to strange trajectories and unexpected forces. The universe would be dimensionally heterogeneous, flat space remaining three-dimensional while curved space gains complexity. To think that dimensionality might not be fixed but variable, increasing where gravity is strong. Protons might have different masses depending on what nuclei they inhabit.